Okay. So I'm going to I'll give like kind of a high level overview of what we've been working on with the team at Google over the past 3 years roughly. So first, kind of set the tone here. If I like kind of take a step back to the dawn of computing, this is like practically the first computer. This is ENIAC from 1946. So in 1946, they were using it for designing nuclear weapons. And then a few years later, they used it to run the world's first numerical weather forecasts. So weather forecasting has been kind of like one of the main uses for computing since kind of like the original uses for computers, like long before we had personal computers and cell phones. And traditionally, this has always been done by solving like physical equations. Basically, we sort of know the equations, a lot of the equations for the Earth's atmosphere. We kind of divide the Earth into a sort of giant grid, and we solve a big simulation problem. This approach has a remarkably successful track record. So this is the accuracy of the forecasts from the European Center for Medium-Range Weather Forecasting, which makes the world's best weather forecasts, starting in 1980 through, this is a paper from about 10 years ago, but it's kind of continued on roughly the same curve. And what you see here is that today, back in, this isn't labeled, but this is a 3-day weather forecast in this blue line here, back in 1980. Today, that yellow line is a 7-day weather forecast. It's about as accurate as the 3-day weather forecast from 40 years ago. So it's been this sort of slow and steady improvement of about like 1 decade, about one day further into the future that we predict accurately per decade over the past 40 years. So something has changed pretty dramatically in weather forecasting just over the last couple years. And that is that AI methods have arrived. A couple years ago when we started working on this, there were a few early experiments at doing sort of AI weather models. The models were pretty bad. They're kind of toy examples. They were about maybe half as accurate as the best sort of traditional physics-based models. And then over the past couple of years, there's really dramatic progress. These models have been getting better and better. And a couple of years ago, some models came out that finally sort of hit this accuracy threshold of the best physics-based models. And it's only kind of continued since then. Now there's like, I don't know, probably a dozen or so models, different dots on there that released from different groups from NVIDIA and Microsoft. A few of these are from Google, the GraphCast and NeuralGCM. And then a bunch of other like startups, even traditional weather modeling agencies have started building AI models. So suddenly it has just really exploded in interest. So today I'm going to be telling you about NeuralGCM, which is by some metrics the world's best weather forecasting model, and which we published recently in a paper that came out in Nature like a few months ago. What NeuralGCM is a little different from most of these other AI weather forecasting models, and that NeuralGCM is actually a blending together of AI and physics. So it's kind of an in-between math, in-between approach. We call this a hybrid model. And so I thought I'd set the tone a little bit talking about kind of the difference between different sort of pure machine learning models versus sort of physics-based models and some of the relative strengths and some of the relative strengths and weaknesses. So on the one hand, we have some of these newfangled machine learning models that are mostly using deep neural networks. And sort of in contrast to sort of more traditional physics-based models, so for weather prediction and climate modeling, and they very different principles. So the machine learning-based models are actually remarkably simple, not a whole lot of code. So something like 5,000 to 10,000 lines of code. So it's not like teeny, but like something that was been built by pretty small teams over like a handful of months have been able to build these models that are sort of very accurate. And that's because they're trained on huge archives of historical weather data. So like literally actually like petabytes of historical weather data that have gone into like these sort of really sort of detailed reconstructions of sort of past weather that are available to train these machine learning models on. And that means the teams that built these models didn't have to know a lot about physics. All they had to do was get the data and to know how to do the deep learning stuff, which is maybe not easy, but doable. And they directly optimized to make accurate weather forecasts. In contrast, sort of the more traditional physics-based approach is a lot more complicated. So these are models that are like 1 million lines of code. They've been developed over decades by like countless like PhD students and like experts in every different like subdomain of like understanding like earth science. Every line of code there is doing some sort of physical process. Like that's simulating raindrops. That's simulating solar radiation going between clouds. That's simulating the like sea ice or the like it just goes on. But that means like actually like very few people actually understand how the whole thing works. It's so incredibly complicated. But it is based on physical principles, and that does mean that in some sense these models are designed to generalize. So and that's actually pretty important for weather and for climate modeling in particular, because in climate modeling we want to understand what's going to happen to the Earth maybe decades from now. We have no data from like future climate of like decades from now, so we need sort of the physics-based models, or we believe the laws of physics will still hold in the future. So that's where the physics-based models come in. And models like NeuralGCM is sort of taking parts of the physics-based models and replacing sort of the parts of the physics-based models that we know well, that we sort of believe in pretty well. And that's, in general, in the physics-based models, that's the fluid simulation part of the models, and selectively replacing parts of the models with AI. So it turns out that the hardest part of physics-based models are modeling, we'll get into this, but it's modeling sort of subgrid processes. So that these models often have a grid spacing of, say, around 100 kilometers on a side, and a lot can happen in 100 kilometers. And none of that detail falls in, all of that is sort of approximated. So we're going to approximate the small scale behavior with neural nets. And that allows us to make, that's kind of the part of the physics-based models that have the most uncertainty. So kind of selectively blending together the physics-based and the AI-based approaches to hopefully have some of the strengths of both sides. We have this hybrid model. We have the traditional fluid solver that uses sort of established sort of techniques for solving moving fluids on a grid. And then we have a neural network that learns all the other terms and the equations that make weather so incredibly hard to model and understand. So that's processes like solar radiation, clouds, raindrops, interactions with ocean and land surface, sort of evaporation of water. All of this stuff is like the majority of the complexity in a traditional weather or climate model. And here we're going to replace all that really complicated stuff, which is a huge amount of code and the equations are not very well understood. We're going to replace it with a neural network that learns it from data. So we're going to kind of put together the traditional solver plus the neural network part and sort of plug it into sort of autoregressively forecast out in time to match, and tuning this model to match historical weather observations from the past 50 years of weather. We have this thing, we wrote the entire thing, sort of including the physics simulator from scratch in an AI framework called JAX. So I'll tell you a little bit why that's important. We're not the first ones to try building a hybrid model, especially for climate. Climate scientists know their models are not accurate enough to understand the impact, to accurately simulate the impact of climate change. So they need better models, and they've been exploring using AI for a long time. Actually, for maybe about the past 5-10 years. But most of these approaches have not worked very well at all. And the problem is, I'll tell you why. And so the problem is that they train these models offline. So they have some model they trust. And here, this part is a dynamical core. That's kind of like the fluid simulator. It's like a million lines of Fortran. So it's like an ancient, really gnarly code. They can't really go inside it very well. So they just kind of capture the outputs. They say, this model is going to have some errors. Let's make a training data set of kind of what the model produces and what it should produce, something from some other data, from maybe a more accurate simulator or some real world data. We're gonna make a bunch of examples for a neural network. And so, but in practice, what that means is they're only training the neural network to predict one step forward in time. It's like the weather model predicts forward like a typical weather model might predict forward like 5 minutes at a time. But what you actually care about is not 5 minutes forward in time. You care about maybe 5-10 days. Actually, a climate model, 5 years, 10 years, 20 years. And that means that when you use these models, there's this gap between what you trained for and what you're doing at inference time. This train test skew means that oftentimes you run these models, and basically a simulator works for maybe a few hours, maybe a few days, and then it just kind of explodes. Like it sees some examples because the simulator, the neural network now sees examples that sees its own mistakes, and it never saw those mistakes in the training data. And so because of that, these traditional models often have like really poor performance when you actually run them. So what we did with NeuralGCM is a little different. We took that dynamical core, that's sort of the guts of the weather model, and we rewrote it. We wrote it in JAX. So the magic of JAX, which is used for building AI models at Google and elsewhere, is that you can optimize through arbitrary code. It supports automatic differentiation. So now what we can do is we can optimize through the collective behavior of neural network plus physics model collectively, and we can do that over many time steps. So we can train the model on if we care about making a 5-day weather forecast, we can actually have the model trained for making a 5-day weather forecast. And that means there's not this gap anymore. and the model, in sort of this online training, produced the model that works really well. And also, so we built this on top of JAX. So it's also, you have like, now you have like a modern like programming language instead of Fortran, and we can use kind of all the JAX magic that makes it a really powerful tool for building like large-scale AI models. A lot of that also incredibly useful for building simulations. We can do these like various like code transformations, and we can sort of very easily distribute our model across a whole bunch of different Google TPUs or GPUs. We can do all sorts of sort of clever tricks like JAX has. Like we have the automatic differentiation, of course, that's the gradient calculation. We have these vectorizing transformations. We can do we have this gradient checkpointing logic, which saves you a lot of, it's a way to trade off extra compute to save memory. And then we compile it with all these like machine learning compilers. So basically, like, we have a pretty small amount of code that we sort of flexibly transform into something that allows us to tune these like really powerful models. So I'll talk a little bit about kind of what we've done with this. Then we'll open up for questions. So kind of the exciting thing about NeuralGCM and what we kind of most focusing on here is we wanted a model that produces predictions that look really realistic. Most prior AI models were just trying to make a better weather forecast. And sometimes making a better weather forecast, you don't have to produce realistic weather. It's like if the goal is to say what is the weather going to be like a week from now or 2 weeks from now, you can say like, well, I think it's going to be about maybe 70 degrees in Palo Alto, and that's probably about right. If you only can make a single number, your best guess is always going to be kind of average. You're gonna like you're not really rewarded for, even if there might be a storm next week. If you predict that on the wrong day, you're gonna have a very large loss in your model. The traditional, most of these deterministic AI models, they tend to make really blurry predictions, and you can kind of see this here. So we have like one of these models on the right here that after 10 days, it's a lot blurrier than on day one for that forecast. So initially it's kind of sharp and then it gets really blurry. In NeuralGCM, in contrast, we've done, I can tell you about this later, but like a bunch of tricks we did, but part of that is we actually can make ensemble weather forecasts, so kind of representing the whole range of different scenarios. So we don't just make one prediction, we predict a whole range of scenarios of what might happen, and they can all be sort of very sharp, realistic-looking examples of weather with like good like weather systems and clouds and hurricanes. And even if you don't get any of them right, on average, they have a very good prediction. That's kind of the secret to how we're able to make these sort of physically realistic and very high-quality weather forecasts that qualitatively look a lot more like weather. And so what you can do with that is you can run this model out for models like this. You can run them out for a week or two for weather forecast. You can also run them out for years and do things closer to climate simulations. And so one example of what we do here is we ran the model for a whole year, and we are simulating tropical cyclones, hurricanes. What you see here is the orange lines are kind of the ground truth where a tropical cyclone occurred in 2020. The blue lines are NeuralGCM. And so you're never going to exactly predict the tropical cyclone in the right place a year in advance. That's not possible. But what you can do with these models is that you can simulate the range of possibilities. So you can say like, where might a tropical cyclone hit? And like how likely is it that, say, in the present ocean conditions, the warmth of the oceans, and the cycle of El Nino, how likely is it that you might have a severe tropical storm that goes through the Southwest, for example, like that terrible Hurricane Helene earlier, I guess, last week. And so that's the sort of thing that we can start to look at now. And quantitatively, NeuralGCM does a very good job of this. So we compared to some climate models, sort of in development climate models from NOAA. So this is a model called XShield, and this is kind of a next generation climate model. So it's actually this is a 3-kilometer resolution model. So it's a really high resolution grid, a very detailed picture of the Earth, very expensive simulation. And NeuralGCM sort of is able to reproduce the average amount of moisture in the atmosphere with about 30 to 40% less air, which is pretty exciting for climate scientists that have been building these models for a very long time. And this is very hard to reduce these errors. It's also much faster. So climate scientists care about, they want their model to be fast, to be practical. You want to simulate, ideally be simulating maybe 10 years in one day of wall clock time. That's what it takes to make a practical, fast enough climate model that you can explore. Because you have to simulate, if you want to understand what might happen in the future, you have to simulate sort of many ranges of scenarios. Like simulate 100 years, and you do it 10 times because there's a lot of uncertainty about all the conditions. So thousands of years of climate to make a useful climate forecast. And NeuralGCM can do this at like about 20 simulated years per day. This model does it at that's 5% of a year per day. So like really slow. It takes a really long time. This model is like 70,000 times faster. It runs on one Google TPU chip versus 13,000 CPUs. It's like a pretty big cluster. And if you ballpark estimate about how expensive this would be, this is like 8 cents to simulate 1 year of climate versus perhaps like $80,000. So like this is $80,000. That's never going to be feasible for actually doing climate simulation. Of course, they're working on trying to make these models faster. They're talking about building like I was at a conference earlier this week. They're talking about building like specialized hardware for climate simulation. We're going to build like a dedicated climate supercomputer. It's still going to be like fantastically expensive, and like they may never actually get to like this. That's really unclear if they'll ever get to the speed they need for the highly accurate simulations. So we also took these models and have been sort of exploring running it out for sort of longer simulations as well. And so this is closer to getting towards what we call a climate projection. That's like looking at climate over multiple decades. So here we did this retrospectively. So I should say, the model we have today is not a full climate model. It's kind of part of a climate model. It's just the atmosphere. So we can only kind of run this retrospectively, but in the past currently, but we can compare to other atmosphere-only climate models. So these are models where you assume that you knew what happened with the ocean. Like you assume you know how warm the ocean is, and then what happens in the atmosphere? How does that vary over time? Here we're comparing to these AMIT models, and these are kind of traditional. These are the sort of traditional climate models that have been developed over the past decades. And these models, and what you see with NeuralGCM is that we reproduce sort of the observed trends in global temperature much more closely than these traditional physics-based models. Now, this is kind of the training data as well, so there's a little bit of a question about whether we, you might say that, well, maybe you're overfitting to observations. I mean, to be fair, the climate models have also been fit, of course, to the past 40 years of weather data too. But if you look into the details of these simulations, what you see is that they're reproducing a whole bunch of different weather patterns, different types of plausible-looking storms, for example. So we get the variability as well. And so this is, I think, pretty exciting for the climate modelers to think about what using these techniques for better climate simulation. And again, the last point here, it's like a fun graphic that we made about how fast these models are comparing NeuralGCM to like the real-time simulation. Their spins 1 time per simulated day here. How fast we're able to simulate things compared to like the operational climate models like CAM6, which is kind of a workhorse climate simulator. I mean, still really expensive, like 1,000 CPUs, and it like kind of slowly moves along. Or this X-Shield thing that's like honestly way too slow for anyone to actually use today for real. Okay, so that's kind of most of my slides. I'm happy to answer questions. But again, in summary, what we did here, this model, so it's very good 15-day weather forecasts. And particularly, it beats the best physics-based models for this task of sort of global weather forecasting and sort of this with sort of probabilistic global weather forecasting, which is the main source of weather forecasts over like this is like these models are like the models you get on your phone basically. Like if you see like a weather forecast, you're looking at the European weather forecast, which is the model we compare against. And we are also able to make like really competitive climate simulations of the Earth's atmosphere. They're not sort of fully realistic yet, but they're able to, in terms of, they're not capturing all processes yet, but they capture the much more realistic weather patterns than the best climate models. And it's a whole lot cheaper and faster. So it's like maybe 1,000, million-fold cheaper to run. And it's a lot simpler too. It's like 20,000 lines of code versus like 400,000 lines of code. So the potential here is to make, and this is true of NeuralGCM, but also this broader field of AI weather and climate models, is to make weather and climate modeling a lot more accessible. So it's like stuff you can run on a laptop, stuff you can sort of interactively explore what might happen to climate instead of being something that like only specialized government centers are able to do. And the hope is that this information can, of course, be useful, as we deal with climate change and sort of a lot of, rapidly changing extreme weather. Okay, a few more things here. Get some links to the paper. We put the code is up on, we open source all the code, and so we've, so this is also sort of freely available.
I was going to say that, like, okay, so traditionally, all the AI weather forecast models now are all trained on ERA5 beta. Mm-hmm. It's the ground truth, right?
Yeah.
But you kind of explained that it was not really like that for NeuralGCM. Is that like, so did you guys generate like your own training data? Is that what that, I kind of didn't understand. I'm not really.
We did, in fact, train this model on We did train it on ERA5. We trained it on the same data sets that most of these AI weather models have been trained on. So it is similar in that respect. I think that maybe what you're getting at is kind of like what would it look like to go beyond training?
I was wondering if it was a little bit different, the approach that you guys use, because I remember you said like you had like the gold spheres instead of like the other ones, and I didn't know.
Yeah, so this is in contrast to a traditional. I mean, we kind of rewrote the weather model. We use this, so it's kind of that's more in contrast, I would say, to the traditional sort of like the way people have been exploring modifying like a traditional physics-based model with AI components. So we didn't just kind of like inject a little bit of TensorFlow in that giant pile of Fortran. We said, okay, let's toss out and try to start from new. So that's honestly a little controversial for the climate scientists because they really like their climate simulation codes. Frankly, the climate simulation codes can do a lot of things that we can't actually do yet, like all sorts of different like hypothetical future climate scenarios. But that was kind of our strategy, kind of bite the bullet and see if like rebuilding from scratch could be helpful.
Well, I was wondering about that hypothetical future stuff, particularly when the climate gets into regimes that haven't been seen before.
Yes.
How does that affect the trained models?
So that's a great question. I mean, so I'll say we did some tests of this. So we can do some tests by just like artificially warming the oceans and see how the model responds. And so what we found is like you get about 2 degrees warmer, the model does fine, about what you'd expect. If you make it 4 degrees warmer, which is like pretty bad climate scenarios, our model does not do well currently. And that's maybe not surprising. We didn't train on that. And there are tactics you could take if you want to make a model generalize better into future climate. So it's like not quite a full climate. That's why I wouldn't call it a climate forecast yet, maybe a climate simulation.
Is the approach itself something that you see adaptable to that, or is that a fundamental?
I think it is very adaptable. I mean, there's a lot of people in the climate modeling community who are very excited about trying to build, integrating climate models with AI, and there are lots of tactics for how to make your your AI model look more, sort of handle the climate simulation things. And it's like one version that would be training on a climate model output. So run a climate simulator for the next 100 years, then train an emulator that now runs 1,000 times faster. That's actually pretty compelling. We wanted to have models that were trained on historical data because because historical data can actually be much more reflective of the real world than other simulation.
I was also wondering, in terms of like you showed a slide there with the differential equation solver and stuff.
Yeah.
I was wondering, are the variables and stuff that go into both the inputs and outputs of, the XTs, are those variables that you have chosen and are interpretable?
Yeah, so that's actually pretty critical, I think, honestly, for all the successful AI weather forecasting models. Everyone who's tried to do this with like a black box approach of like, say, I'm just going to like learn what's the right representation of the atmosphere. I don't know. I'll throw it into a neural network. Let the neural network learn. That has never been successful, to my knowledge. And so so we actually simulate things on a big 3D grid that's like vertically goes up 32 levels in the atmosphere, and that simulates each of these is a different weather variable like wind or temperature or humidity. And these are the exact variables that are in a traditional weather or climate model. I think so far that seems to be pretty key. In theory, maybe you can find the latent space representation of the atmosphere, but no one has been able to make that work yet.
So you are just representing the conditions in a grid.
Oh yeah.
But it's a 3D grid.
So the representation actually is pretty traditional. The difference is that we just have like a much more accurate model for how it evolves from time step to time step.
Wait, 2 questions. On this slide, so for the initial stage, what parameters did you use?
In our case, what we do is we actually take this past climate reconstruction called ERA5, and we say we're going to use that as sort of the problem is that weather data is so complicated. There are all these different satellites and weather stations and balloons and so somebody has already done this European Weather Forecasting Center, already did the hard work of sort of trying to integrate all those into some estimate of the current state of the world. And they did that going back for the past 80 years. So we use their model kind of for the initial conditions and kind of like the targets for our model. And then we just feed it through to make predictions.
And the second question was about the tropical cycling that you showed the comparison with graphs.
Yes.
So those are this single ensemble number, or the average that you're showing here?
I mean, this is just like a single example. We also, we can run this out for an ensemble as well, and that's pretty useful for understanding. This is just one example of like what might happen, and we run it for a whole year. But we do have like a stochastic model. So we also looked at looking at like a 1 week weather forecast for tropical cyclones. There's a lot of uncertainty about where it might go, and so we also did that as well, and sort of run out different scenarios. But this example is just kind of one realization of that we're showing.
Did you also tried to see if you could increase resolution? Until what point did you get the same cycles per years per second?
Yeah, so the model every time, so our model looks a lot like sort of like a, I mean, at the core of it, it's actually still doing like the physics-based simulator that we wrote is still the slowest part of the simulation. And that means that the speed of our model is limited by the resolution. So it's actually pretty terrible scaling. Every time you double the resolution in a physics-based simulator, it runs 8 times slower. So we tried really hard to push the resolution because every time we increased the resolution, the model got more accurate. But at the end, it was like, okay, this is something that runs on like 250 TPUs for a month to train the model, and it's like, we just can't do more than that. Like the next doubling is now you're like, now it would be, I don't know, it'd be like 2,000 TPUs for a month, and that's like starting to actually get expensive even at Google.
So the limitation is essentially the training part, not the...
Yeah, so this is actually an interesting difference compared to traditional like weather and climate models, is that they're mostly slow to make predictions. In our case, the hard part is doing training a model because you have to make so many weather forecasts. You have to make like thousands of years of weather forecasts to train the model.
I'm also curious about how do you think the model is like scalable in terms of like a new weather variable? Like for example, saying that you want to take the simulation on some like more subtle weather variable, saying the turbulence or the wind shear. If you are not going to scale up the resolution, you mentioned the runtime complexity is like the O3, and then what could be happen that if you want to like adapt it to a more like subtle weather variable?
The weather variables that we model, there are a few more weather variables in the atmosphere, and the stuff we miss, like we don't do ozone, we don't do aerosols, we don't do smoke. We don't do like greenhouse gases. This is like honestly most of the core weather variables. Like that stuff, like the particulate matter, like that stuff maybe matters especially on like really long like climate simulations. But for weather forecasting, we have almost everything you need. You might care, for example, about making a prediction about, that's another thing we haven't done. It's like you might care about predicting weather on the ground, for example. And like we honestly we kind of intentionally didn't do that yet. So our model doesn't directly predict rain, for example. That's a pretty important weather variable. But we kind of have all the information you need to do that. So like everything, we know everything's going on in the atmosphere. And so if you just kind of track that, like from that, you should be able to predict. If you care about, and this is like what happens in traditional weather models, is they also don't like predict like weather at every location on the ground. They don't predict whether it's like foggy in San Francisco because that's way too local. But you can kind of use them as inputs to say like, okay, the general conditions are it's a very hot day in California, therefore the fog should have burned off in San Francisco today. And that's so realistically you'd have to build like another kind of a downstream model that kind of that makes like a local weather prediction on top of this.
As you mentioned, like at the end of the day, the NeuralGCM is like still has a PDE solver, so they get limited by the runtime complexity and space-time complexity of the grid. So how do you see is the future of your research and the research overall in this weather forecast? So
yeah, so I would say that like in terms of sort of modeling the large scale, sort of like the predictability of the Earth's atmosphere, like the AI models they may, in some cases, the AI model might make sort of slightly higher resolution predictions, but it's not actually sort of more doing a better job of representing like the weather patterns. Like the accuracy there is about the same. They're also not much faster either, to be honest. I think most of these AI models implicitly are actually modeling the Earth on a pretty coarse grid, even if they make predictions at very fine points. So it's interesting to see where this goes. One version is trying to scale this up. Personally, I think a more interesting area to explore is going maybe two directions. One is sort of more local weather, and like regional scale weather is like useful for a lot of use cases, and building those models, kind of models that can represent like what's happening on the very local level is something that we haven't seen a lot of in AI weather prediction, mostly because there isn't the data for that. Like there's not good data about like local weather conditions. That's much harder than global weather, interestingly. The other direction would be going out to longer time scales, like in the direction of if you want models that can predict seasons to years in advance, and there you have to do a lot more than the atmosphere. Like honestly, this atmosphere model is good enough, but what you need is now you need to model the oceans and sort of like feedbacks with like land and ice, and like it gets more complicated. But I think that those other processes are going to be where we're going to see like what you need to get sort of more bang for your buck in that direction.